One of the foundational understandings necessary for calculus is this idea of a limit. Now, we're just going to take a very loose, informal approach to these. You will certainly formalize the definitions and the understandings of a limit in your future math classes and calculus and so forth. Today, I just want to get our feet wet and make sure we have a basic understanding of it. So we're not going to talk about a formal definition. We're going to talk about the informal idea. Right? So these are very informal terms. But simply put, a limit, and we typically talk about it with a function, relative to a function, the limit of a function is a description of the function's behavior around a specific x value. Let's go ahead and write that down. So a limit of a function is a description of the function's behavior at a certain x value. To do this, we look at its behavior around that x value. And what do I mean by looking around the x value? It turns out that when we talk about a limit, we really don't care exactly what's going on at that location. It sort of seems contradictory to this definition, but it's sort of like if you want to describe how the wind is blowing, you don't look at the exact actual wind because it's impossible. You sort of look at the effects, the leaves blowing, so on and so forth. So if I want to study the limit of a particular function at, say, x equals 2, I actually don't look exactly directly at x equals 2. You look at the x values around x equals 2 to sort of see the effects that the function has. I think this will be a lot easier to see with a particular example. So for example, we'll just take this for take a look at this function. Consider the function, say f of x equals, I don't know, x minus 1 over x squared minus 1. And here's the question. And I'm going to phrase it in the way that we typically say it in math. What is the limit of f of x, so of this function, as x approaches, say, the number 1? Now, mathematicians, we don't want to constantly write these long sentences over and over and over. What is the limit of this function as x approaches the other function? So there is a notation for it. So the notation for that previous sentence, i.e., is this. We abbreviate limit as lim. Below that, we do x arrow and then whatever number we're looking at. So in this case, we're looking at x equals 1. And then to the side here, this doesn't have to be parentheses. In the side here, we put the actual function itself. So x minus 1 over x squared minus 1. So this symbols here, this notation is asking exactly this question. Well, actually, not entirely. Instead of saying f of x, instead of putting f of x right here, I actually wrote out the whole function. But you could easily put f of x in there. So you can see why the idea of a limit, even though, again, we're only talking about the rough idea, the informal idea, you can see why the idea of a limit, we really don't care what happens exactly at that x value, because it's impossible to use x equals 1. Try, go ahead, give it a shot. Plug in x equals 1 here, you're going to get 0 in the denominator, and we all know that we can't divide by 0 in mathematics. So we can't even look at the function value. The function value is actually undefined at the x value we're looking at. So how are we supposed to do this? Well, the idea of a limit, again, is to see what the function does around x equals 1. So what we could do is just make a table of values and take a look at x values that are really, really close to 1. Now there's an infinite amount of numbers you can pick. What I like to do is I like to organize my numbers so they're all like increasing or decreasing. So let's make two sets of tables here. Let's do x values here, but they're going to be x values less than 1. And let's do x values here, but they're greater than 1. And again, the idea is that I want to look at x values that are close to the one that we're interested in this case, close to 1. So x is less than 1. Technically, -5 is less than 1, but it doesn't really give me a lot of evidence to the behavior of the function around x equals 1. So we really want to choose numbers that are really close to 1. Say, for example, 0.5 is close to 1, but 0.9 is also closer to 1. 0.99 is also closer to 1. 0.999 is also closer to 1. 0.9999 is also closer to 1. You guys sort of get the idea. Take a look at the sequence of x values going from top to bottom. Do you see how all of these numbers are less than 1, but they're getting closer and closer and closer to 1? It's sort of the sequences that we're talking about in Unit 12. And that's sort of the idea. You want to look at the behavior of the function as you're getting closer and closer and closer to the x value in question. Let's go ahead and take a look at the other side, right? Let's choose numbers that are bigger than 1, but are getting closer and closer and closer to 1. Say, for example, 1.5, or maybe 1.1, or 1.01, or 1.001, or 1.0001, and so on and so on and so forth. And I can just keep going and going and going. Okay. So again, note that in this table, this is a sequence of x values that are bigger than 1, but they're getting closer and closer and closer to 1. So let's just go ahead and do some plug and chug. I'll save you guys some time. I did it beforehand. But all you're going to do is, one at a time, take these x values, plug into x, and see what you get. So let's do 0.5. So if we were to plug in a 0.5 into the function, you're going to get 0.666 repeating, so let's say 0.667. If you plug in a 0.9, you're going to get 0.526316. Plug in a 0.99, you're going to get 0.502513. Plug in a 0.999, you're going to get 0.500250. Plug in a 0.9999, you're going to get a 0.500025. Interesting. Let's do the other table. Plug in a 1.5 and you're going to get a 0.4, pretty much exact. Plug in a 1.1, you're going to get a 0.476190. Plug in a 1.01, you get a 0.497512. Plug in a 1.001, you're going to get a 0.499750. Plug in a 1.0001, you're going to get 0.499975. Whew, a lot of plugging and chugging. So how do we answer this question? Again, the informal idea of a limit is describing the behavior as x gets to this number, not when x equals that number. We really don't care what happens when x equals that number. We care about what the function is doing as x gets towards that number. And in these two columns, hopefully you can agree with me, these x values are getting closer and closer to 1. These x values are getting closer and closer to 1. So to answer this question, you have to look at what the function is doing, namely the y values. So as the x gets closer and closer to 1, what do the y values tend to be doing? Where does the y value tend to be going? Same thing with this graph here. As x gets closer and closer to 1, although, this is not a nice sequence. It's not arithmetic or geometric. We can't come up with a nice formula for it. But if you were to, squint your eyes, make an educated guess, these numbers here, as you keep going and going and going, what value do they tend to be approaching? What value do you think they're trying to settle on? Well, on the basis of this chart here, I hope it's not a hard thing to see. We can see that as x gets closer to 1, the function outputs gets closer to 0.5, 1/2. Symbolically, we can see that the limit as x approaches 1 of x minus 1 over x squared minus 1 is 0.5. And that's exactly how we would write it. And we can see that with the tables here. So that's it. That's sort of the rough idea of a limit. A limit is just analyzing the behavior of a function around a particular x value. But we use the behavior around that particular x value to make a definitive statement about the behavior at that x value. Let me say it again. In this chart here, we didn't look at what happens when x equals 1. As a matter of fact, we couldn't. It's mathematically impossible to plug in an x equals 1 in there and get a defined value. What a limit does is it sort of says, okay, I can't see what goes on at x equals 1. It's like saying I can't see the wind. But I want to sort of see what happens around x equals 1. I want to see the leaves moving so I can describe the behavior of the wind. Oh, the leaves are blowing to the left, so I can say that the wind is blowing to the left. Oh, the leaves are blowing up, I can say the wind is blowing up. Likewise, when I take a look at these x values that are getting closer to 1, I can see that the y values are getting closer to 0.5. Same thing with this chart here. So I can say, even though I can't tell what's happening exactly at x equals 1, the overall function behavior, aka the limit as you get closer and closer to 1, is 1/2. So that is sort of like the general idea of what a limit is. It's describing the behavior of a function, describing what the function is trying to do at that x value without actually looking at what at that specific x value, because sometimes you can't. Notice how we did the tables. We did two tables here, right? And we sort of separate the x values in a particular manner. Let me erase these arrows here. All of these x values were numbers that were less than 1, approaching 1 here. If you sort of take a look at a number line here, I'm going to draw a number line 0. Where should I put this? Let's put this. I'll put it up here. And I'll do it in a different color to make sure that you guys know it's separate from the notes. We should know, based upon how the number line works, that numbers get bigger towards the right and numbers are smaller towards the left. So all of these x values were smaller than 1, that's smaller than what we were, smaller than the x value we were looking at. So we would say that these numbers are to the left of 1. These numbers are getting closer and closer to 1, but since they're less than 1, they were getting closer from the left. You can see in this picture here in the number line that 0.5, 0.9, 0.999, getting closer and closer to 1, we were approaching from the left. Likewise, we were approaching from the right when we were looking at x values bigger than 1, but getting closer and closer and closer. The notation for these, because we did it separately, is we use a superscript plus or superscript minus to represent left or right. So in this particular case here, I would have written the limit as x approaches 1 for this particular table. Since we chose to use x values that were smaller than 1, it was approaching from the left. So we would say, based upon this table alone, just this table, we are ignoring this table. Based upon the left table alone, we would say the limit as x approaches 1 from the left, and this is the notation that we use, of the function is 0.5. But of course, from here we would say the limit as x approaches 1 from the right, because those are the x values that we chose to look at, of the function is also 0.5. Notice how they reached, yeah, I think that's proper English. Notice how they reached the same conclusion. Notice how they reached the same conclusion. Yeah, it just sounds wrong in my head. So notice how these two tables concluded the same thing. Let's say that. They both confirm that whether or not you go from the left or whether or not you go from the right, you get the same behavior. The behavior is the function's approaching 0.5. And that's sort of another important idea when it comes to limits. So again, I'm going to speak things in informal terms. You can formalize it later in calculus. But an informal idea, when looking, let's say this. For the limit as x approaches some number c of some function, when looking at x values smaller than c, we call it a left-handed or left-sided limit, denoted by limit as x approaches c with a little negative superscript. Similarly, when looking at x values bigger than c, we call it a right-handed or right-sided limit, denoted by limit as x approaches c with the superscript plus. Now this is one of the key tenements. It's not really a theorem. I guess you can call it a theorem, but this is one of the key tenement ideas of limits and an idea of calculus. In order for a limit to exist, in order for a limit to have an answer, to have an actual defined answer, the limit as x approaches whatever number from the left must always be the same as the limit as x approaches from the right. So basically, if you are to declare that the overall limit exists, those two tables that you made, one from the left and one from the right, must coexist, must coincide. They must be copacetic. If this is the case, you can say that the overall limit exists without any superscripts. Okay. So that's a key important idea, that just because you can successfully fill out one table doesn't necessarily mean that the entire limit exists. You have to fill out the other table to see what's going on here. Let's do an example here. I don't know. Let's do one more example. Say I ask you to find the limit as x approaches 0 of the square root of x squared plus 9 minus 3 on the outside over x squared. And you can see here how, again, the idea of a limit, we really don't care what happens at exactly x equals 0, because we can't even plug in 0 even if we wanted to, because we get a 0 in the denominator. So we're going to have to use a table. Again, I'm going to draw those two tables because we have to look at both sides of the limit. So I'm going to choose x values that are smaller than 0, and I'm going to choose x values that are bigger than 0. I don't know. Say, oh, I mean, we really could choose whatever numbers that we want. Um, I don't know. Let's do from the left, say -1, -0.5, -0.00, I don't know, 0.5, -0.001. I don't know. These, you can see these are numbers smaller than 0, getting closer and closer and closer to it. How many numbers do you pick? That's usually a common question I get. I don't know. Just choose enough so you can see a pattern. Choose enough so you can see if the sequence is converging somewhere. And then greater than 1, greater than 0, I don't know. Just choose a positive twin. So 1, 0.5, 0.05, 0.01 maybe. So let's just do plug and chug. So let's go to the left table. If I plug in a -1, you should get a 0.16228. Plug in a -0.5, you get a 0.16553. Plug in a -0.05, that's 0.16667. Plug in a 0.001, you get 0.1666667. Let's plug in a 1 here. You get a 0.16288. Plug in a 0.5. Well, I guess it should all be the same because all those x's are being squared. Yeah, they're all going to be the same because in the function the x is being squared. Right. So from this, you can see that yes, both the left-handed limit and the right-handed limit does exist. These numbers do seem to be converging towards one number. If I had to guess, it looks like it's converging to 0.1666666 repeated. So you don't have to write this. I'm writing this down from the notes. It looks like the limit as x approaches 0 of the function from the left is the same as the limit as x approaches 0 from the right, which equals 0.166 repeating. Therefore, we can conclude, again, this line here is extra. I'm putting for the notes. You don't really have to write it. This is what you need to write down, that the limit as x approaches 0 of f of x is, and 0.16 repeating, we should know repeated decimals, is 1/6. Right. So from this table, so what do I expect to see? Well, from this two tables there, that's the key here. That is what tells you what the answer is. From those two tables, you can conclude this guy right here. Right. So that's the idea of a limit. It's a simple concept. It's looking at the effects of whatever it is you're interested in. It's looking at the effects of the wind on leaves. It's looking at the effects of x values as you approach another value on the overall function. And you should be adept at this if I give you an equation or if I give you a graph, because applying the idea graphically is the same as equation-wise. So let's go ahead and take a look at this example here. Now, I suck at graphing, so bear with me. We're going to have to do some sketching here. Suppose the graph of f of x is given below. So let's try to make a somewhat accurate, it's not going to be perfect, but let's make it somewhat accurate. No, let's not do this. I don't want this. I only want the first quadrant. So do we have the first quadrant? Hey, here we go. Well, let's just put some negatives in here too. I guess I'll extend it like this. There you go. And let's see here. Let's try to do some tick marks to be somewhat accurate. Let's go up to, I don't know, 5, 2, 3, 4, 5. It doesn't have to be a big picture. 1, 2, 3, 4. I guess it's not square. And let's say at 2, 3, there's an open circle here, and then from the left it just swishes up. Let's just do that. And let's say there's an open circle at 2, 1, and there's an open circle at 5, 2. 1, 2, 3, 4, 5, 2. 2, 3, 4, 5. Make it easier to see. So 5, 2, there's an open circle. So let's say it swishes this way and continues that way, but at 5, 1, the actual point is there. So suppose I gave you this graph, and I asked you to find letter A, the limit as x approaches 2 from the left of f of x. Letter B, the limit as x approaches, oh, I don't know, 2 from the right of f of x. Letter C, the limit as x approaches 2 overall of f of x. So to do this, you just have to utilize the idea of a limit. You're looking at the behavior where the graph is going without actually getting to the x value. So let's do letter A. What is the graph doing as x approaches 2 from the left? So here's x equals 2. I'm going to draw it in. Here's x equals 2. I don't want to do dashed lines. I'll go ahead and do a solid line. So to find out the behavior as x approaches 2 from the left, you have to basically trace the graph starting on the left and approaching x equals 2. So if I were to highlight the graph, so I'm not up here, I'm not down here, I have to start on the graph, and I'm going to approach 2 from the left. What y value does the graph tend to is getting towards? Even though it's an open circle means it doesn't exist, that particular value, you have to look at the overall behavior. Overall, what y value does it seem to be approaching? Well, I hope everyone can see that it's approaching y equals 3. Even though there's an open circle there, all of the points to the left of 2 is trying to get to y equals 3, and that's the idea of a limit. So here, this would equal 3. So if we do the same thing for part B, approach the y equals 2 from the right, so I'm going to trace the graph from the right and going leftwards to 2. What y value is it trying to get towards? Well, it's trying to get to y equals 1. Question C, what is the overall limit? Well, remember the general idea is that the overall limit only exists if the left and right-sided limits exist. Since these are two different numbers, it simply does not exist. Right. Just as sort of a bonus, what if I asked you to observe the limit as x approaches 5? So as x approaches 5, from the left, we get 2. From the right, we also get 2. Now notice the actual value is 1. So right, this is a solid circle, so that is legitimately the exact actual value. But we wouldn't say the limit is 1. We would say that the limit is 2 because the other points around it is trying to get to 2. So that's sort of the key thing that I want to really hammer in your minds. When it comes to the idea of limits, it's not what happens exactly at the point, it's what happens around the x value as you approach from the left and to the right. Let's do one last example just because I noticed there's some piecewise on the practice. Doing the piecewise examples should be pretty simple and straightforward. Suppose I asked you, let f of x equals, it'll be a piecewise function. Say 2x squared whenever x is less than 1, and say it's 4 minus x whenever x is greater than or equal to 1. Right. And I'm going to ask you to find the limit as x approaches 1 of f of x. Well, to do this, you have to do the left and the right-sided limit, so let's go ahead and do that. So solution. What is the limit as x approaches 1 from the left of f of x. Well, we're going to make a table, right? Of x less than 1, and I'm approaching it from the left, so let's say it's, you know, I don't know, 0.9, 0.99, 0.999, 0.9999. Now, when it comes to piecewise functions, you have to remember which function you're going to use. So since I want x values that are less than 1, hopefully everyone agrees that's the top function, because the top function only works when x is less than 1. So for the function values here, I'm just going to use the 2x squared. So let me go ahead and grab my calculator. And let's just start plugging and chugging, right? So when I plug in a 0.9, we are going to get 1.62. Maybe I should do this in a different color. 1.62. If I plug in a 0.99, I get a 1.9602. Plug in a 0.999, 1.996, 0.9999, get a 1.9996. I think everyone's sort of getting the general idea. What is the left-handed limit? If I had to guess, it looks like it's approaching the number 2. So let's go ahead and do the right-handed limit. The limit as x approaches 1 from the right of f of x. So again, I'm just going to choose x values that are bigger than 1, but are approaching it, say 1.1, 1.01, 1.001, 1.0001. And since I'm choosing x values that are bigger than 1, according to this piecewise function, I have to use this part of the function, 4 minus x. So that's what I'm going to be plugging into. I'm no longer plugging into 2x squared. I'm going to be plugging it into 4 minus x. So let me grab my calculator. So plug in a 1.1, you're going to get a 2.9. 1.01, you're going to get a 2.99. 1.001, you're going to get a 2.999. 1.00001, oops, too many O's. 1.0001, 3 zeros, is 2.9999. Oh shoot, I should have done this in a different color. Hold on. There we go. The joys of digital ink. This guy here, let's change to blue. I want to change to blue. There we go. This guy here, let's change to blue. This guy here, let's change to blue. Okay. So from this table, hopefully it looks very obvious. We can make an educated guess that this is approaching 3. Well, since the left and right-sided limits are not the same, here is our overall answer. Therefore, the limit as x approaches 1 overall, no plus or minus, just 1 overall, of f of x does not exist. Right, so limits. It's just analyzing the behavior of where the function is going by looking at x values around the target x value. To do that, you simply make a whole bunch of tables. Or, if they give you a graph, you just trace the graph from the left or to the right. So there is your intro to limits. Good luck.